All right, so we're continuing on with 1.1 function relationships. Yesterday we did a brain dump. Do y'all remember doing that? Where we wrote our sticky notes, what we remember from Algebra 1, and we talked about that we're going to be talking about linear, quadratic, and exponential functions. So we're reviewing linear, building on quadratics, and introducing exponential, correct? All right, so to do that, we're going to kind of define them, what they are, starting with our linear function, okay? So in your notebook, you can do it horizontally, vertically, however you want, but you're going to create this, what's called a Frayer model in your notes, okay? All right, on page 3, exactly. So on page 3, it could be whatever you want. It could be the whole page, you can draw it. They're your notes. I did mine vertically in my notes, and I just did the whole page. I can model what mine looks like. So I just did mine vertically. So this is what mine looks like in my notebooks. It's really up to you however you want to do it. You can do it small, big. You know better how you write. I just let it take up the whole page because I'm not putting anything else on it. Okay. You need mine. Pretty good. There you go. All right. Are we ready to start filling it in, or we're still sketching it out? I moved it drawing a circle in the line. My bad. My bad. All right. So for linear function, we're going to write the formal definition. Okay. We're writing our formal definition. And the formal definition, well, semi-formal, is going to be a relationship between two quantities. And those quantities are x and y, some unknowns, right? Some variables. With a constant rate of change. That's what makes something linear. There is a constant rate of change. Questions about the definition? No? All right. Our characteristics. What is the constant rate of change called? Good job. So constant rate of change equals our slope. The ways to represent slope, we have m, right? M equals, that's our y2 minus y1 over. Yep. And then when you're looking at it graphically, what's our little short way of remembering how to find it? Rise over run. My S got a little funky there. Okay. All in our brain, right? We already knew that. Cool. So when you look at the graph, the key thing about a linear function is the graph is a non-vertical. Graph is a non-vertical line. That's why when we have a vertical line, we say it's an undefined, right? And there are 3 equations. So the equations that represent a line. Can someone tell me what is the most common one? Y equals mx plus b. The equation of the line. Okay. Does anyone know the standard form? AX plus BY equals C. Does that look familiar? And the least used is our point slope, which is y minus y1 equals m times x minus x1. So those are the 3 ways that I can represent the equation of a line. Y equals mx plus b, and then y minus y1 equals m times x minus x1. All right, so what I want you to do is to take a moment and you're going to create your own example of a linear equation based on what you know. So it can be, try to do our 4 representations. So we have algebraic, we have table, we have graph, and we have words, right? So graphically, what could it be? What does it look like? Algebraically, what does it look like? You can create any model that you want. I'll give you a moment to do so, and then I'll do mine. Draw a graph. Yes. All right. Can someone give me one of their examples for a function, for an algebraic representation? I like it. Perfect. Right? And I know it's linear. I have a slope and I have a y-intercept, right? I just drew a line of some sort in my notes. Yeah, there's my graph. Beautiful. It's a non-vertical line happening for you. Did anyone do a word example? There you go. An hourly rate, right? Or job rate. So I'm gonna write hourly or weekly rate, right? That's good. And then did anyone create a table? Oh, what are your numbers in your table?
X is 2, 4, and 6, and Y is 4, 8, 12.
Do we all see what his rate of change is? What are we doing? Times 2, we're doubling, right? Our constant rate of change is, we're doubling. We're adding 4 every time. We're doubling. Yeah. All right. Last thing I want to talk about is that as we go through our class, we're going to see slope and another shorthand way of writing slope. We may not use m as much, but you may see change in y over change in x. Okay. This is called delta. So I know you're like triangle. In math and science, this represents delta. So delta y over delta x. Okay. It means change. So you may not see me always write y2 minus y1 over x2 minus x1. That's because I would probably write delta y over delta x. Okay. Delta again means change. All right. Non-examples. You can do it. Could have done anything for a non-example. Someone give me a non-example. What? A little, yeah. A little sad face. Awesome. I'm assuming yours is prettier than mine. But here's my little sad face. Anyone else did another non-example? You did a table? What are your table values?
It says all my x's are 3,
Oh, good one.
and then 8, 4, and 6.
Perfect. There we go. Cool. Easy. All right, let's move on to our page 4. We're going to do our quadratic. So now we're on page 4. So we're going to do our quadratic function. And here's our definition. It's a relationship, again, between two quantities. And what are those two quantities called? X and Y. Good old X and Y. And this time, though, it's with a linear rate of change. So instead of a constant, we have a linear rate of change. Why? How did you number? You must not have started with 0.
0,
1,
1,
2, then 3.
4,
Then just do your 4 on the other side. It's as long as all 3 are there, we'll figure it out. So you're doing your Frayer model should be between pages 3 and 5. All right. Characteristics. So let's talk about what linear rate of change would look like. So if we have a linear rate of change, that means that my change is my x times something plus something. So to get from my x to my y, I'm multiplying by something and adding something. I'm sorry, to get from my y to my y, it's a change in between there. I was like, wait, I said that weird. So from y to y, it's going to be multiplied, then added to get to that change. And then our shape is our parabola, our parabola. If you need help spelling it, that's how I spelled it. I kept remember how to spell it. Parabola. All right. You're either going to have a happy parabola. That means that you have a positive quadratic. Or you're going to have a sad parabola, which means that you have a negative quadratic. And we're going to talk about the equations that represent a quadratic. So an equation in any of these forms. First, we're going to start with standard, which is ax squared plus bx plus c. Does that look familiar? I forgot my f of x. Let's f of x equals. Our next form is going to be called our vertex form. So we have f of x equals a times x minus h squared plus k. And our last form is our root form, which is f of x equals a times x minus r1, which is root 1, times x minus r2, which is root 2. So we have standard, vertex, and root. The one that you probably used the most often or saw was standard. All right, so based on our boards yesterday, we need a little more guidance with quadratics. So we're going to do our examples together. Is that cool? All right. So for examples, we're going to do our function first. F of x equals. Someone give me a number. 3. So we have 3x squared. Someone give me a number. 2x. Someone give me a number. 5. That's a quadratic. It's quadratic because my highest power is a 2. We see that? All right. Can anyone think of a real world example of a quadratic situation? A bridge, an arch. There you go. Can have an arch and a bridge. Yeah. Another one is trajectory, right? Anytime you're kicking or throwing a ball. Is that spell trajectory? I think so. It looks good to me. That's because the theory is if something goes up, it must do what? Come down, right? So over time, it's gonna go and then come back down. All right. A table. We'll do the parent function. 1, 2, 3, 4, which gives us 1, 4, 9, and 16. And then you can draw your own graph, however you want. All right, non-examples. Anything that doesn't fit in the example box, have at it. A line, a straight line. What if I have y equals x to the third plus x squared? It's not, because is the 2 my highest power anymore? Nope. I can also have, that's definitely not one. Anything that doesn't fit in my example box. Questions about our quadratic? Easy enough? All right, last but not least, the one we know nothing about is our exponential. And this is going to be on page 5. Okay, for exponential, we have, it's a relationship between, I can't write, between 2 quantities. And of course, they're going to be x and y. Now, this is different. It's with a constant ratio. Of change. So we're looking at a constant ratio of change. That's saying to get from one y to the next, I am multiplying by the same number. So for linear, we had a, what was linear? What was this? Constant rate of change. That means I'm adding or subtracting the same amount to get from one y to the next, right? Okay. With our quadratic, we have what? Linear rate of change. That means to get from one y to the other, I am multiplying and or adding to get from one y to the next. Now we're at exponential, and exponential is a constant ratio. Constant ratio is saying I am multiplying to get from one to the next. Got it? All right. So constant ratio is our key thing here, and that means that we are multiplying. Do we all know that division is the same as multiplication, right? It's just multiplication of a fraction. That when you're dividing, you're just multiplying by a fraction. So when I say multiplying, that also means that it could be division. Does that make sense? Okay. And we're going to talk about, it can either graphically, you can have a growth. And we read graphs from left to right. So growth means that I'm starting off slow, but then I grow exponentially. Or we could have a decay, which means I start off high and then I, decline. Okay, the next is what type of behavior? It has a special type of behavior. It's called asymptotic. I'll let you be the judge of how to say it. That's how it's spelled. Asymptotic, is that how we would say that? Asymptotic behavior. Okay, what this means is that there is a boundary line in my function. Some type of boundary exists. And there's only one equation for it, and it's f of x equals a times b to the x. A is going to be our initial. And b is going to be our ratio. Okay, so we're going to do our examples together. So our examples here, we're just going to start off with the most common used. And that's going to be f of x equals 2 to the x. Okay, so for f of x equals 2 to the x, our initial, if there is no number being multiplied, it's cast with a friendly 1 there, right? So it's 1. So our initial value is 1. Okay. And then our ratio is going to be 2 because that's our base. So when you look at the graph, the table, I'm sorry. When you say initial, that means you're starting at 0. And we're going to go 0, 1, 2, and 3. What is our initial value? 1. Cast for the friendly 1. Okay. Another thing to remember is anything to the 0 power equals what? 1. Anything to the 0 power is 1. 1 million to the 0 is 1. Okay. That's one of your exponent laws and rules. All right. Now 2 to the 1 is 2. 2 to the 2 is 2 to the 3 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 is 8. 2 to the 3 means you have 2 times 2 times 2, which equals 8. So 2 to the 3rd power is 8. Yeah. Okay. Our constant ratio, that means that to get from one y to the next, I'm multiplying by the same thing. So how am I getting from this y to this? How am I getting from this y to that? How am I getting from this to y to that? 2. Do we see the constant ratio? All right. That's what makes this exponential. Yes. Okay. All right. Graphically, you have a boundary line. In this case, my boundary line is going to be my x-axis, because notice I did not touch it or cross it. A real world problem that probably involves exponential growth would probably be stocks, the stock market. Because of the growth and decay, how it can rapidly change at any moment in the stocks, right? All right, so therefore, anything that we've talked about outside of this box is going to be our non-example. I can have y equals x plus 5. I can have y equals negative x squared. I can just draw a constant line. Anything that is not in the example box is a non-example. Okay, so tomorrow you're going to be using your notes to do your Desmos activity. Okay, that's going to be our part 3, and it's a Desmos sort. Okay, if you wanted to get started on it, I did send it already to you on your Google Classroom, but it's a Desmos sort, and basically you're going to be using your notes, your Frayer model, to decide whether the graph, the words, the situation, if it's linear, quadratic, exponential, or neither, and you're going to categorize them. Okay, so that's what we're going to do before we continue tomorrow. Cool. So tomorrow when we come in, we have our calculator scavenger hunt to finish. We're then going to do our Desmos sort, And then we will continue from there. Cool? All right. Great job. Any questions, comments, or concerns? Do you feel a little more informed than doing the brain dump yesterday? Yeah, okay, good.